1, I'm not going to worry about my units because I'm running out of space, times the temperature. It's at 25 Celsius. 25 plus 273 is going to be 298 Kelvin. All right, so again, I've got 300 times about 0.1, so it's going to be about 30, times 0.2, which is 1/5. So 1/5 of 30 would be about 6, times 2, and it's negative. So 6 times negative 2, I'm going to estimate on here about negative 12. And my calculator's on my phone. This is kind of embarrassing. Negative 12 bar. Oh, grab my other machine. All right, let's check this out in the magic number box. So, negative 2 times 0.2 times 0.0831 times 298. See how good my estimation skills. Negative 9.9. I think that's close enough to 12 to call it good. All right, so negative 9.9 bar. Beautiful. All right. Find the water potential of the cell. Oh, of course. All right, so I've got to do the exact same thing again. The only thing that's going to be different in here is this this concentration, because we still got our R values the same. The temperature's the same. We're still dealing with salt. So all we would have to do here is replace the 0.2 with a 0.4. Do I have to do any math here? No, I don't. 0.2 to 0.4, what's that going to do? It's going to double it. Booyah. All right, so the water potential. Oh, tricky, Freeman. The water potential of the cell is probably at equilibrium because it's got two different things going on. It's got the solute potential plus the pressure potential equaling this up top. Aha! Okay, so this is kind of an interesting math problem because of what values I happen to use. But I already know the solute potential on the inside of the cell. It's double this value because I've got double the concentration. So 9.9 times 2 is going to be 19.8, and it's going to be negative. We've got more disorder on the inside of the cell, so there's a lower water potential. Remember, lower water potential means that stuff's going to be moving in. But because things aren't moving in anymore, it is at equilibrium with the outside. Negative 19.8 plus the pressure potential of the cell must be equal to negative 9.9, the outside. All right, and so this won't always be the case. It's because I've selected bad units that worked out really easy for my math. So negative 19.8 plus, what's the pressure in the cell? Now the pressure in this case, it's got to be a positive number, right? We're taking 19.8. We've got to get it up to negative 9.9, and pressure is going to be a positive number because we can't have negative pressure. There's no such thing in physics as a negative pressure. Things don't suck; they blow. And so 19.8 plus 9.9 bar. All right, so the total water potential of the cell is going to be equal to the outside. I already kind of answered that part. So this right here is the answer for the outside of the cell, and because it is at equilibrium, my answer is negative 9.9 bar because it's at equilibrium. Find the pressure. Where did I do? Next page, find the pressure potential of the cell. Oh, well, I don't have to do that on the next page because I just did it. We know the solute potential of the cell is going to be twice as much, but it's negative. We figured this out by subtraction. It's got to be 9.9 bar. Oh, look at this. I left myself a bunch of space. The inside solute potential is negative 19.8 bar. The outside was negative 9.9 bar. These will not always be doubles. This happens to be because Freeman picked 0.4 and 0.2. So I have, oh, look at this. I have my logic. Water potential on the outside equals water potential inside at equilibrium. Therefore, the water potential I could say the total. Total inside is going to be the same as the outside. So the total water potential is the solute plus the pressure potential. In this case, negative 9.9 equals negative 19.8 plus 9.9. This value's got to be positive. This value's got to be negative. Those two work out. Okay. Going right along. Water potential in a particular tissue is negative 2.6 bar. What's going to happen if we put it in a 0.2 molar salt solution? This is where it really gets real. All right. So we know. I don't know. I wrote this problem like 6 hours ago. So the water potential is equal to the solute potential plus the pressure potential. And that is only going to be the case at equilibrium. Where there, no, this is not necessarily the case. The outside and inside bits are the same at equilibrium, but the water potential is something that exists all the time. So, yeah, let's figure out what the water potential is now, because it says when this is placed. So when it is placed, there's no pressure because the cell hasn't swollen up yet. I think that's got to be our assumption on this problem. So the water potential inside the cell is going to be the solute potential, and then all we got to do is figure out our water potential inside and our water potential outside, remembering that it's going to go from high water potential to low water potential. We just got to figure out what it is. So we know that the water potential in the tissue is negative 2.6. So this is negative 2.6 bar. Not 26, but so negative 2.6 versus, let's find what it is in the solution. We got 28 Celsius, 0.2 molar. So, and it's salt again. All right, so solute potential equals negative I times C times R times T. Freeman's getting good at this. All right. The rust is getting cleaned off. So negative I, that's going to be negative 2 because it's sodium chloride. It splits into two pieces times the molarity, which was 0.2 moles per liter, times R, which is 0.0831, times the temperature, 28 Celsius. Why did I do that to myself? 301 Kelvin. Again, I can estimate this. 0.0831 times 301, this is about 0.1, so that's about 30. 30 times 1/5 is again 6. Negative 2 times 6 is going to be negative 12. I think I just did this on the last problem. Idiot. So I should be 9.9. Yeah, 2 times 0.2 times 0.08. Oh, the temperature value is different. 301. Oh, shoot. It's very close. All right. 10. Booyah. All right. So negative 2.6 versus negative 10. What is the water going to do? Well, it is a salt solution, which helps us out. But we know it's going to go from high. In this case, 2.6 is high water potential. Negative 10 is very low. So it's going to go from the high to the low. It's going to move out of the cell. Sweet. Last problem. Yes. Last problem. Find the pressure potential of a cell with solute potential of minus 5 bar that is in equilibrium with a solution with water potential minus 2.5 bar. Oh, interesting. Okay. So we know the solution must be equal to, oops, I'm just going to call that out, equals the solute potential plus the pressure potential. In this case, the cell has a solute potential of negative 5 bar. Negative 5 bar. equals the solution with water potential minus 2.5 bar. Sweet. All right, so minus 2.5 equals minus 5 plus what value? How did I make all my math problems exactly half? Oh, because the worksheets that we do in class will not have this because I'm going to copy them from somebody else. All right, plus, so negative 5, how do I get to 2.5? From negative 5, I've got to add 2.5 to it. It's logic. All right, I hope you enjoy. I hope you didn't enjoy water potential, but if you could enjoy a tiny bit of it, at least you appreciate the poor potatoes that we tortured.